Welcome to this session. Today, we'll be tackling LeetCode problem number 2199, titled Find All People with Secret. We'll explore how to determine which people discover the secret through specific meetings. Let's dive in. This problem is about tracking how a secret spreads among a group of people. You are given n, the total number of people, labeled from 0 to n1. Initially, person 0 and a specified person, first person, know the secret. The spread of the secret is determined by a list of meetings. Each meeting specifies two people who meet at a particular time, and during the meeting, the secret can be shared if either of them knows it. Importantly, the secret can also propagate indirectly through intermediate people. Your goal is to return a list of all the people who know the secret by the end. The order of the people in the output does not matter. Consider the first example. Here, n is 6, first person is 1, and the meetings array specifies the times and pairs of people who meet. Initially, only persons 0 and 1 know the secret. At time 1, person 0 meets person 2, and person 1 meets person 3, so persons 2 and 3 learn the secret. At time 2, person 2 meets person 3, but since both already know the secret, nothing changes. At time 3, person 3 meets person 4, spreading the secret to person 4. By the end, persons 0, 1, 2, 3, 4 know the secret. In the second example, n is 4, first person is 3, and the meetings array specifies 3 interactions. Initially, persons 0 and 3 know the secret. At time 1, person 0 meets person 3, but since they both already know the secret, no further propagation occurs. At time 2, person 1 meets person 2, but neither knows the secret, so nothing changes. At time 3, person 3 meets person 1, spreading the secret to person 1. However, person 1 cannot propagate the secret further. By the end, only persons 0, 3 know the secret. In the third example, n is 5, first person is 2, and the meetings array lists 3 interactions. Initially, persons 0 and 2 know the secret. At time 1, person 2 meets person 3, so person 3 learns the secret. At time 2, person 1 meets person 4, but neither of them knows the secret, so nothing changes. By the end, persons 0, 2, 3 know the secret. There are several edge cases to consider. First, if n is 1, there is only one person, so the output is 0. If there are no meetings, the secret remains with persons 0 and first person. When meetings form disconnected groups, the secret cannot propagate between these groups. If many meetings occur at the same time, it is critical to process them together. Lastly, if no one meets person 0 or first person, the secret does not spread beyond them. These scenarios highlight the importance of carefully handling edge cases in your solution. To solve the problem Find All People with Secret, we need to determine which individuals eventually learn the secret after a series of time-sensitive meetings. The problem can be visualized as a graph, where people are the nodes and meetings are the edges. One approach we considered is the brute force solution. The intuition here is straightforward: simulate the spread of the secret by iterating through all meetings. If either participant in a meeting knows the secret, the other person is added to the set of people who know it. While this method is easy to conceptualize, it has significant drawbacks. The time complexity is n squared, because we may need to repeatedly iterate through all meetings. This makes it inefficient for large inputs. Additionally, the lack of structure in handling meeting times means meetings may be unnecessarily reprocessed multiple times, making this approach impractical for real-world scenarios. Overall, it's a simple but inefficient solution, especially for larger datasets. A more efficient solution involves using a union-find or disjoint set union structure. The key intuition here is to treat people as nodes and meetings as edges, grouping them by the time they occur. By processing meetings chronologically, we can connect individuals who meet at the same time into temporary groups using union find. This allows us to propagate the secret within each connected group. The implementation begins by sorting the meetings array by time. For each time group, we use union find to create connected components of people who meet simultaneously. After processing a time group, the secret is propagated to everyone in the connected group. There are several advantages to this approach. Sorting the meetings ensures we respect the chronological constraints, while union-find operations allow efficient grouping and propagation. The time complexity is O, m asterisk log m, plus n asterisk alpha n, where m is the number of meetings and alpha n is the inverse Ackermann function, which grows extremely slowly. The space complexity is O, n, for the union-find structure. This approach avoids unnecessary reprocessing and scales efficiently, making it well-suited for the problem. Another strategy we considered is breadth-first search, or BFS. Here, we model the problem as a graph traversal. Each person is a node, and meetings form edges between them. We can propagate the secret using BFS, starting from the initial holders, person 0 and first person. The meetings are grouped by time in an adjacency list, and BFS is performed for each connected component in chronological order. While this method is intuitive and has a similar time complexity to union find, it requires additional bookkeeping to handle the time constraints effectively. This can make it cumbersome for larger datasets with repetitive time groups. Ultimately, we chose the union find approach as our solution. It strikes a balance between simplicity, clarity, and efficiency. By sorting meetings by time and grouping people who meet simultaneously, we isolate time groups and propagate secrets locally. This avoids unnecessary reprocessing and ensures correctness. Compared to the brute force method, union find is significantly faster and eliminates redundant iterations. While BFS is conceptually similar, union find is cleaner and more scalable. With its ability to handle large inputs while adhering to the problem constraints, the union find approach provides an elegant and performant solution. In this problem, we need to determine all the people who eventually learn a secret after a series of meetings. Initially, the secret is known to person 0 and one additional person, referred to as first person. The key input here is the meetings array, where each meeting specifies 2 people and the time they meet. The goal is to propagate the secret based on these meetings, while ensuring that the order of meetings is respected. This makes time a critical factor in the problem. There are several challenges. First, we must process meetings in chronological order to maintain proper propagation. Second, for people meeting at the same time, we need a way to efficiently determine who can share the secret within those groups. Finally, we need a scalable approach to handle large inputs without redundant computations. With this framework in mind, we can now explore the steps to solve the problem effectively. To tackle the problem, the first step is to sort the meetings array by time. This ensures that we process the meetings in the correct chronological order, which is essential for accurately propagating the secret. Next, we initialize a set called known, which starts with person 0 and first person, as these individuals know the secret at the beginning. After this, we iterate through the meetings, grouping together all meetings that occur at the same time. This grouping is important because it allows us to handle all interactions happening simultaneously, preventing premature propagation to unrelated groups. For each group of meetings at the same time, we construct a graph where the nodes represent people, and an edge exists between 2 people if they meet. This graph helps us identify connected components, which are groups of people who can potentially share the secret during that time step. Once the graph for a time group is built, we use a traversal method such as breadth-first search, BFS, or depth-first search, DFS, to propagate the secret. The key idea is to examine each connected component in the graph. If any person in the component is already in the known set, it means the secret can propagate to the entire component. We then mark all individuals in that component as knowing the secret. After processing a time group, the newly identified individuals are added to the master known set, ensuring that the information is up to date for subsequent time steps. Finally, after all meetings are processed, we output the known set as a list. It's important to note the insights that make this solution work. Respecting the time order of meetings is critical, as out-of-order propagation would lead to incorrect results. Additionally, using graph connectivity ensures that we only process relevant groups of people at each time step, while BFS or DFS allows us to efficiently traverse those groups. The algorithm relies on several key data structures. The known set is used to track all individuals who currently know the secret, and it supports fast lookups and insertions. For each time group, we rebuild a graph representation using a dictionary, where the keys are individuals and the values are the people they interact with during that time. This allows us to efficiently determine connected components. The meetings list, once sorted, provides a sequential way to process interactions in chronological order. In terms of complexity, sorting the meetings takes m log m, where m is the number of meetings. For each group, building the graph and performing BFS or DFS takes m plus n, where n is the number of people. Overall, the time complexity is m log m plus n. Space complexity involves storing the graph in the known set, leading to a requirement of n plus m. Edge cases include scenarios with no meetings, where the result is simply the initial known set, or disjoint groups where the secret doesn't propagate between isolated clusters. The algorithm is optimized to handle large inputs efficiently. Let's apply the algorithm to an example. Suppose we have n equals 4, meetings equals 0, 2, 1, 1, 3, 2, 2, 3, 3, and first person equals 1. First, we sort the meetings by time, resulting in 0, 2, 1, 1, 3, 2, 2, 3, 3. We initialize the known set with 0, 1. At time 1, we build the graph 0, 2, 2, 0. The connected component 0, 2 contains person 0, who knows the secret, so we add 2 to known. At time 2, the graph is 1, 3, 3, 1. Here, the component 1, 3 includes person 1, so we add 3 to known. At time 3, the graph is 2, 3, 3, 2. Both 2 and 3 already know the secret, so there's no change. Finally, we return 0, 1, 2, 3 as the output, representing all individuals who learned the secret. To solve this problem, we start by importing the necessary modules. The default dict helps us create a graph structure, and deque is used for efficient breadth-first search. Inside the solution class, the findAllPeople method begins by sorting the meetings based on their time. This ensures that we process all meetings in chronological order, which is essential for accurately tracking how the secret spreads over time. Next, we initialize a secret_graph using defaultDict list. This graph will store all connections between people who are part of the same meeting at a specific time. For each meeting, represented by the pair of people X and Y in the meeting time, we populate the graph with the connections for that time slot. Now, we know that person 0 and the first person are the initial holders of the secret. So, we create a set called knows_secret to keep track of everyone who knows the secret at any point. This set is initialized with these two individuals. Then, as we process meetings in chronological order, we prepare to handle the interactions for each specific time slot. For each time, a temporary graph is created to represent the connections between people who meet during that time. This graph uses a similar structure to the main graph but is scoped to just the current time slot. We also initialize a visited set to track people we've already processed during our search. For each person in the temporary graph, we use a breadth-first search to explore all individuals connected to them. This involves initializing a queue with the current person and a set called component to store the connected group. As we dequeue each individual, we check if they've been visited. If not, we mark them as visited, add them to the component, and enqueue all their neighbors who haven't been visited yet. This process continues until we've traversed all nodes in the connected component. Once we have a complete component, we check if there's any overlap between this group and the knows_secret set. If even one person in the component knows the secret, the entire component now learns the secret. We achieve this by updating the knows_secret set with all individuals from the component. After processing all meetings, the knows_secret set contains everyone who knows the secret, and we return it as a list. This ensures the solution is both efficient and correct, as we carefully handle each group of meetings and maintain the chronological order of events. Here, we begin by importing the necessary packages and defining our solution class with the method findAllPeople. The method takes 3 parameters: the total number of people, a 2D array of meeting details, and the first person who learns the secret. To ensure we process the meetings in chronological order, we sort the meetings array based on the time value, which is the third element in each subarray. Next, we create a hash set called knowSecret to track all individuals who know the secret. Initially, this set includes person 0, who starts with the secret, and the first person passed to the method. We then use a hash map to group meetings by their respective time values. For each meeting, we add it to a list in the map, where the key is the meeting time. By organizing meetings this way, we can process them efficiently, one time group at a time. Now, we iterate through each time group of meetings. For each group, we create a temporary graph to represent the connections between people meeting at that specific time. Each meeting is represented as an edge in the graph, connecting two people. Using a hash map, we build this graph by adding each person as a key and their meeting partners as values in a list. With the graph constructed, we proceed to identify connected components using a breadth-first search, or BFS. We initialize a visited set to ensure we don't revisit nodes, and for every unvisited person in the graph, we start a BFS. During the BFS, we maintain a queue to explore the graph and a component set to store all the people connected in this particular group. As we explore, we add each person and their connections to these structures. The goal here is to find clusters of people who are directly or indirectly connected through meetings. If any person in the current connected component already knows the secret, we update the no-secret set to include everyone in that component. This ensures that the secret spreads to all connected individuals at this time step. After processing all time groups and their corresponding meetings, the no-secret set contains all people who have learned the secret. Finally, we return this set as a list, which represents the result of our method. By combining sorting, graph construction, and BFS, we efficiently determine who learns the secret while processing meetings in chronological order and respecting their time dependencies. To solve this problem, let's start with a basic example where we have 4 people and a series of meetings. The goal is to determine who knows the secret by the end. First, we sort the meetings based on their time, which results in the list remaining as is 0, 1, 1, 1, 2, 2, 2, 3, 3. Next, we initialize our variables. The knows_secret set starts with persons 0 and 1 because person 1 was directly informed by person 0. We also build a secret_graph that maps each time to the corresponding meetings. At time 1, we have meeting 0, 1, at time 2, meeting 1, 2, and at time 3, meeting 2, 3. Now, we process the first meeting at time 1. Here, we create a temporary graph representing the connections between persons 0 and 1, 0, 1, 1, 0. Using BFS, we find the connected components starting from person 0, which includes persons 0 and 1. This means both of them know the secret at this point. Since there's no change in the knows_secret set after the first meeting, it remains 0, 1. Next, we process the meeting at time 2, where persons 1 and 2 meet. The temporary graph for this meeting is 1, 2, 2, 1. Again, we perform BFS to find the connected components starting from person 1, which includes persons 1 and 2. Since person 1 already knows the secret, we update the knows_secret set to include person 2, resulting in 0, 1, 2. Now, at time 3, persons 2 and 3 meet. The temporary graph for this meeting is 2, 3, 3, 2. Using BFS starting from person 2, we find that the connected component includes persons 2 and 3. Since person 2 knows the secret, we update the knows_secret set to include person 3 as well. By the end of all meetings, everyone knows the secret, so the final output is 0, 1, 2, 3. In this second example, we have 6 people and a more complex meeting structure, which includes disconnected subgroups. First, we sort the meetings by time, resulting in the same order 0, 1, 1, 2, 3, 2, 4, 5, 3, 1, 2, 4. The knows_secret set is initialized with persons 0 and 1, as they are directly informed, and the secret_graph maps each time to its corresponding meetings. At time 1, persons 0 and 1 meet. The temporary graph for this meeting is 0, 1, 1, 0. Using BFS starting from person 0, the connected component includes persons 0 and 1. Both of them already know the secret, so the knows_secret set remains unchanged at 0, 1. Next, at time 2, persons 2 and 3 meet. The temporary graph for this meeting is 2, 3, 3, 2. Using BFS starting from person 2, the connected component includes persons 2 and 3. However, there is no overlap between this group and the knows_secret set, so no updates are made. Then, at time 3, persons 4 and 5 meet. The temporary graph for this meeting is 4, 5, 5, 4. BFS starting from person 4 identifies a connected component of persons 4 and 5, but again, there is no intersection with the knows_secret set, so no updates occur. Finally, at time 4, persons 1 and 2 meet. The temporary graph is 1, 2, 2, 1. Using BFS starting from person 1, we find a connected component of persons 1 and 2. Since person 1 knows the secret, we update the knows_secret set to include person 2, resulting in 0, 1, 2. By the end, only persons 0, 1, and 2 know the secret, so the final output is 0, 1, 2. Now, let's consider an example where the secret does not propagate beyond the first informed person. Here, we have 3 people and only one meeting at time 1 between persons 1 and 2. The knows_secret set starts with persons 0 and 2, as person 2 was directly informed, and the secret_graph is initialized with the single meeting at time 1, 1, 1, 2. At time 1, the temporary graph for the meeting between persons 1 and 2 is 1, 2, 2, 1. Using BFS starting from person 1, we find the connected component 1, 2. However, since neither person 1 nor person 2 intersects with the knows_secret set, the secret does not propagate further. Thus, the knows_secret set remains 0, 2, and the final output is 0, 2. To understand the time complexity of our solution, let's break it down step by step. The first step involves sorting the meetings array based on their timestamps. Since the array contains m elements, the sorting operation takes m*log m time. After sorting, we group the meetings by their timestamps using a dictionary called secret_graph. This grouping process involves iterating through the meetings array once, which is an O-M operation. These steps lay the foundation for processing the data efficiently in the subsequent steps. Next, we process the meetings grouped by timestamps. For each unique timestamp, we handle the meetings that occur at that specific time. Let's say there are t unique timestamps. For each timestamp, we first build a temporary graph, temp_graph, representing the adjacency list for the people involved in these meetings. If there are k meetings at this timestamp, constructing this graph takes k time. After building the graph, we identify the connected components using breadth-first search, or BFS. In the worst case, BFS visits all the people in the component once, which takes c time if the component size is c. When we sum up the BFS operations across all timestamps, the total time is proportional to m, since the number of people involved in meetings is at most m. Finally, within each connected component, we check if anyone knows the secret. This operation also takes c time for a component of size c, and overall, this step is bounded by m. When we combine all these steps, the dominant term in the time complexity is the sorting step, which is m*log m. The subsequent steps, graph construction, BFS, and secret updates, are all bounded by m. Therefore, the overall time complexity of the solution is m*log m. Now, moving on to space complexity, we identify the main contributors. The first is graph storage. The temporary graph, temp_graph, holds the adjacency list for people involved in meetings at a specific timestamp. In the worst case, this graph contains m edges, assuming all meetings occur simultaneously. Hence, the space required for graph storage is m. Additionally, we maintain a visited set during BFS to track the nodes we've processed. In the worst case, this set contains all n people, requiring n space. Another contributor to space complexity is the BFS queue and the component set, which store people in the current connected component. The size of these structures is determined by the largest connected component, which in the worst case could contain all n people, leading to a space requirement of n. We also have the knows_secret set, which keeps track of the people who know the secret. Since the size of this set is at most n, it requires n space. Finally, the input meetings array itself uses m space. When we sum up these contributions, the dominant terms are the graph storage, BFS structures, and the input storage. The overall space complexity of the solution is therefore m plus n. To put these complexities into perspective, let's compare the optimized approach with a brute force approach. In a naive solution, we might simulate the propagation of the secret for each meeting sequentially. For every meeting, we'd update the knowledge status for all n people. This would result in a time complexity of O(m*n) in the worst case, which becomes infeasible for large inputs. Our optimized solution, on the other hand, sorts the meetings and processes them by timestamps, using graph traversal to propagate the secret within connected components. This reduces the time complexity to O(m*log m, making it significantly faster for larger values of m and n. While the optimized solution requires extra space for graph storage in BFS structures, this trade-off is acceptable given the substantial improvement in time complexity. The space complexity of O(m+n) is a reasonable cost for the efficiency gained. Now let's analyze the algorithm under different scenarios. In the best case, there are very few meetings, and the connected components formed are small. Here, the BFS operations are minimal, and the time complexity is dominated by the sorting step, resulting in O(m*log m). In an average case, the meetings are distributed across various timestamps, and the algorithm processes each timestamp efficiently, maintaining the overall complexity of O(m*log m). In the worst case, all meetings occur at the same timestamp, leading to a single large graph. While BFS would traverse all n people in this scenario, the dominant term still remains the sorting step, so the time complexity remains O(m*log m). This consistency across cases demonstrates the robustness of the optimized solution. One of the most common pitfalls in solving this problem is processing meetings in the order they're given without sorting them by time. Since the propagation of the secret depends on the sequence of meetings, failing to sort can cause incorrect results. Another mistake is not accounting for connected components within the same time window. Meetings that occur simultaneously should be treated as part of the same group, and ignoring this can lead to incomplete propagation of the secret among people who are actually connected at that time. Additionally, while DFS or BFS are valid techniques for traversing connected components, using them naively without considering time constraints can result in significant inefficiencies, particularly for large datasets. Lastly, edge cases like isolated nodes, people who don't participate in any meetings, or ensuring that the person with the initial secret is always included in the result are often overlooked, leading to incorrect outputs. Another mistake to watch out for is ignoring constraints on meeting times or the IDs of people involved. For example, people IDs must remain within valid bounds, and meeting times must be non-negative. Overlooking these constraints can result in runtime errors, particularly in edge cases. Now, when discussing this problem in an interview, you can impress your interviewer by framing it as a dynamic graph problem. Here, meetings act as edges that appear in time order, and this perspective demonstrates a structured approach to problem solving. It's also important to emphasize an optimal traversal strategy. Grouping and processing meetings by time, combined with using UnionFind to analyze connected components efficiently, can make your solution stand out. Be ready to explain how your approach handles edge cases like no meetings at all meetings occurring at the same time, or a single isolated individual. Lastly, understanding the time complexity trade-offs is key. Sorting the meetings involves O(m*log m, while UnionFind operations are highly efficient with amortized O(alpha)n, making the solution scalable even for large inputs. This problem also shares similarities with several related problems, which can deepen your understanding of the underlying concepts. For example, LeetCode 684, Redundant Connection, focuses on identifying cycles in an undirected graph using UnionFind, which is similar to grouping people in this problem. LeetCode 839, Similar String Groups, involves grouping strings based on similarity, which is analogous to finding connected components. LeetCode 1101, The Earliest Moment When Everyone Becomes Friends, is another graph problem that deals with time-ordered connections and uses UnionFind to track when all individuals are connected. Finally, LeetCode 323, Number of Connected Components in an Undirected Graph, is a foundational problem that helps build an understanding of graph connectivity, making it a great resource to revisit when preparing for this type of question. There are several approaches to solving this problem, each with its own strengths and trade-offs. The UnionFind method is the most recommended as it is highly efficient for grouping connected components and propagating the secret. In this approach, sorting meetings dominates the overall complexity, but it requires additional space for the parent and rank arrays. Alternatively, BFS or DFS can be used to explore connected components. However, these methods are less efficient when the graph has many nodes and edges, as they require repeated traversal for each time window. Lastly, a simulation-based approach directly iterates over meetings to update who knows the secret. While this method is intuitive, it becomes highly inefficient for large inputs because of redundant checks and the lack of optimization for connected components. Understanding these trade-offs will help you choose the best strategy for the problem at hand. Great work! We've summarized the approach to solving Find All People with Secret and highlighted key algorithmic takeaways. Remember, practicing problems like this helps sharpen your graph and optimization skills. Thanks for watching, and be sure to stay tuned for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!